In this video, we're going to look at an example problem using the chi-square goodness of fit test. I'm going to keep it simple in that our nominal variable is only going to have two categories, so it's a binary variable, and we're going to look at this difference between the proportions that we observe in our data from what we would expect under the null hypothesis. A chi-square goodness of fit test. So here we have our chi-square goodness of fit test. I'm going to say a public health agency finds that, historically at least, 65% of adults between the ages of 60 and 70 years old are compliant with taking their antihypertensive medication as described. So our population is clearly 60 to 70-year-olds and they are on medication for hypertension. To verify that the current compliance proportions have changed, a random sample of 200 subjects taking antihypertensive medication is selected from this described population. And the survey of these individuals find that 118 are compliant, and that means 82 are not compliant. 200 minus 118 gives me 82. Tester claim that the population proportions have changed at the 5% level of significance. So I've already summarized, at least did a summary of what we have here with all the values that we will require for this chi-square goodness of fit test. So I've got step 0 for our 7-step process, starting at step 0. And so I'm going to let P be the proportion of the population that are compliant. And so that means the proportion that's not compliant will be 1 minus P. This is a binary variable. Our categorical variable only has two categories. And when that happens, I'm just going to say that this estimate, so the sample proportion, it's 118 over 200, 118 over the, divided by those 200 individuals in our study, that gives me a 0.59. And I've got to kind of figure out how different is 0.59 from 65, 0.65. But if that is the proportion of people taking, the proportion of people who are not compliant would be 1 minus P hat. Or you can just think about it as the 82 divided by 200, and that leaves me with 41, 0.41. So these are my two observations, but they are the proportions of the two observations. Of course, when we calculate our test statistic, we want the frequency. So we actually want that 118 and that 82. So what we would write, as part still of my summary, I'm going to write that the observed, and I'll put subscript here, compliant. So my observed values for my two categories, the compliant and non-compliant, I've got 118 and 82. Now, if we look at this null hypothesis, 0.65, meaning 0.35 for the second category, the non-compliant category, I can work out what my two expected frequencies are going to be, the expected frequency for each category. I'll take the 0.65 under the null hypothesis, multiply that by 200. So if I expect under the null hypothesis that 65% of people are compliant and I have 200 individuals, 0.65 times 200 gives me 130. And of course, I can say 200 minus 130 gives me 170, but also I can think about the proportion under the null hypothesis who are not compliant must be 35%, 0.35. And if I have 200 individuals, of course it has to be 0.35 times 200 gives me 70. So these are my expected frequencies, and there I have my two observed frequencies, and that's what I'm going to need for this test. So I can write the expected subscript, I should say, compliant 130, and expected non-compliant is 70. So there we go. 118 versus 30, 82 versus 70. What I observe and what I would expect under the null hypothesis. And there we go. Let's think of step number 1. And that is going to be our population parameters. And I'm going to say P underscript, I'm just going to say let's make it compliant is and I'm going to write this out the long way. So I'm saying little p subscript compliant, so the proportion compliant, that is the proportion of 60 to 70-year-olds who are compliant with their antihypertensive medication. And P subscript non-compliant is the proportion of 60 to 70-year-olds that's in the population who are not compliant with their antihypertension medication, implying that my population is only people who are on antihypertensive medication. So let's think of step number 2. Step number 2 are going to be about my hypothesis, my claim. So under the null hypothesis, we're going to say that the proportion of the population of 60 to 70-year-olds who take antihypertensive medication who are compliant, so I'm going to call that P subscript compliant, just to be pedantic, that's going to be 0.65, and then the P for the non-compliant equals 0.35. So I'm going to write all of them, and if you have more than 2 categories, write out all the categories. And if I say the claim is, I'm just going to simply say not the null hypothesis, that it is not these proportions. That's really all you have to do, and that's quite acceptable to write that. So let's look at step number 3. Step number 3, we are all about the level of significance. And we were told to test this at the 5% level of significance. So let's say alpha equals 0.05. Let's look at step number 4. What test are we going to use? So what test are we going to use? What's the assumptions for the use of that test? Well, I'm going to say we're going to use the chi-square goodness of fit test. Can I do this? Let's think about it. I have nominal variables, a nominal variable or a variable with a nominal level of measurement. In this instance, it's binary. There are only 2 of them. If I do look at my expected values, so if we go back 1 page and I look at these expected values, they've got to be at least 5 each. And of course, I've got much more than that. So I'm fine using the chi-square goodness of fit test. Let's do step number 5. And that is going to be our test statistic. Now I'm going to write that out in green because I like to put my definitions and all my equations in green. So I'm going to say x squared is going to be the sum over all these terms. I'm going to start at a counter at 1, and then I'm going to go all the way up to k, where k is the number of categories. In this instance, it's just going to be 2. So I'm going to only have 2 terms, when I is 1, and then when I is 2. And I'm going to have the observed values minus the expected values, and I'm going to square that. And I'm going to divide by the expected values. So all with a little subscript I, so it's going to be observed for the one group minus the expected for that group squared, divided by the expected frequency for that group, go on to the next group. Its observed value minus its expected value squared divided by the expected value. And I know this x squared is going to be described by the chi-square distribution on a given degree of freedom. And our degree of freedom here is very simply going to be k minus 1. So let's see if we can do this calculation. Now we've had the numbers already. So let's say x squared, oh, that's not the pen I want to use. So let's calculate this. We're going to say that x squared equals, now I've got to remember what those values were. So for that compliant group in our observed values, we had 118 of them, but we expected 130 under the null hypothesis for the compliant group. I'm going to square that. Where did my ruler go? There, it's hiding from me. Let's divide this by 130. 130. Now I'm going to go on. That was for I equals 1. Now to go to group number 2 for the second term. And remember, we observed 82 people were non-compliant, but we expected from the null hypothesis for there to be, what was that value? It was 70. So 70 squared, and I'm going to divide that by 70. And if you plug these values into your calculator, see what value for x squared you get. I get 3.1648, something like that, 484. I think that is what we have. That is our x squared statistic. It's an expression of how different is what we observe from what we would expect under the null hypothesis. So in step number 6, we're going to make a decision. So we need a decision rule. And what we're going to go for is the critical value approach. Let's write that, critical value approach. So for the critical value approach, we need an x squared statistic, and this one has got to be on a single degree of freedom. 1 degree of freedom, I've got k is 2 categories, minus 1 is 1. And I want it to be at 0.95. Now, please look in the description down below. There'll be a link to a video that how you can use Google Sheets or any kind of spreadsheet software to calculate these critical values. And if you calculate that critical value, we get 3.84. You can leave it at 3.84. That is our critical value. And if we now look at our x squared statistic for our data, it's 3.16, and it is smaller. So I'm going to say that my chi-square statistic is not larger than this critical chi, critical, let's write that, try and write it at least, critical. There's my critical value, and my x squared statistic is not more, so I'm going to, not more than the critical value, so I'm going to say fail to reject the null hypothesis. Fail to reject the null hypothesis. So if we do want to visualize this, remember these are all the possible x squared values that we can have. So these are all possible x squared values under the null hypothesis. Also linked down below to a video where I show you how we use simulation to simulate all these possible x squared values and to show that this model, this distribution on that given degree of freedom is an excellent fit for the simulated data. So have a look out for that. What we are suggesting is, if we look at this, remember this starts at 0, there's going to be a critical value, maybe around about here, and that value out there is going to be 3.84 of the x squared values. This here will be the least probable 5%. This area under the curve here is 5%. This is a probability density function that creates this curve. So the area under this curve is 1. And so if I go beyond this point, I'm going to be in this region where I find the 5% least probable x squared values. But we are not. We are at 3. What was our value? 3.16. So we are out here, and that is in this region where I would find 95% of my x squared values under the null hypothesis, and that's why we put the 0.95 there. We've come 0.95 of the area under the curve across to get to this point, and beyond that there will only be 5% of the values. So we have not gone beyond the critical value, and we failed to reject the null hypothesis. So if we look at step number 7, that is going to be our conclusion. And I'm going to write this. So I've written, there is not enough evidence in the data at the 5% level of significance to show that the population of 60 to 70-year-olds who are compliant with their antihypertensive medication is not 65%. I don't have enough evidence to show that it's not 65%. So we are still with this null hypothesis. Nothing has changed. So that's how it is. Very easy to do a chi-square test, and the 7 steps that we follow for our hypothesis testing.